Good day. You are welcome to another chemistry session. Today we shall be considering the topic chemical equilibrium. Objective: at the end of this lesson, the students will be able to give some example of reversible reactions, write chemical equations for reversible reactions, define the equilibrium states, state equilibrium law, write equilibrium constants expressions for reactions, state Le Chatelier's principle, and use the Le Chatelier's principle to explain the effects of concentration change, pressure, temperature on the equilibrium position and the equilibrium constants of a reversible reaction. State some applications of equilibrium. Now, reversible reaction. Reversible reactions are reactions that do not proceed to completion, and the conversion of product to reactant is also possible under a set of reaction conditions. They are represented by a reversible sign between the reactant and the product. Reactions in which the reactant go virtually to give product and there is no tendency for products to revert to the reactant are called irreversible reaction. Example: the reaction of magnesium with dilute hydrochloric acid to give magnesium chloride and hydrogen gas. Example of reversible reaction include the decomposition of copper 2 sulfate pentahydrate to give copper 2 sulfate and 5 moles of water, and also ammonium chloride to give reversibly as the ammonia and hydrogen chloride gas. Reversible reactions and the equilibrium states. When a chemical reaction occurs spontaneously, it continues until a state of dynamic equilibrium is reached, in which both the forward and reverse reactions are taking place at the same time. The concentrations of the reactants and products no longer changing with time. The reaction is said to be at equilibrium, or that a state of equilibrium has been reached. This equilibrium can only be established in a sealed system where no of equilibrium has been reached. Chemicals can enter or leave the system. Such a system is called a closed system. The equilibrium state remains unless it is disturbed. The equilibrium state can be approached from the reactants or product's direction. The equilibrium state is a dynamic state in which there is no net change in properties such as the density or concentration of the various parts of the system. At equilibrium state, the free energy change is equal to 0. That is, delta G equals to 0. The reversible reaction and the equilibrium constant. Now, there is a fixed relationship at a given temperature between the molar concentration of the product and the reactant in the equilibrium mixture. The above is the equilibrium law. For a reaction of the form A plus B to give reversibly C and D all in gaseous phase, so the Kc will be written as concentration of C multiplied by D over concentration of A multiplied by concentration of B, which is equal to the concentration of the product over the concentration of the reactant, where the Kc is equals to the equilibrium constants in terms of concentration. From the above, you can see that the equilibrium constant Kc is an index of how far the reaction goes in the direction of C and D. A very high value of Kc implies that the reaction goes virtually to completion. Very small values of Kc implies that the reaction does not go far in favor of C and D. Now let us look at a real equation or real reaction. Hydrogen gas reacting with iodine to give 2 moles of hydrogen iodide. So the Kc can be written in the form concentration of hydrogen iodide raised to the power of 2 over concentration of hydrogen gas multiplied by the concentration of iodine. Another example that you can see is in the formation of ammonia. Nitrogen gas plus 3 moles of hydrogen to give 2 moles of ammonia. And so the Kc will be written as the concentration of ammonia raised to power 2 over the concentration of nitrogen multiplied by the concentration of hydrogen raised to the power of 3. Note that the molar concentration are raised to the power of the reactant coefficient in the equation. A correctly balanced equation is required to enable you write the correct equation for Kc. For gases, we can also write the equilibrium constant expression using the partial pressure of gases. Now, in the above reactions, Kp we use for partial pressure here will now be partial pressure of hydrogen iodide raised to the power of 2 over the partial pressure of hydrogen multiplied by the partial pressure of iodine. Kp and Kc are not equal but are related. The unit of Kp and Kc depend on the particular reaction that is considered. Thank you. I will see you again. Now, welcome back. Now, we want to look at the factors affecting equilibrium position. Now, the factors that affect the equilibrium position. Now, these are the conditions that will alter the position of the equilibrium. These are 1. Concentration of the reactants and the product. 2. Change in pressure. And 3. Temperature change. The effect on the equilibrium state caused by a change of a certain condition of the reaction is predicted by the Le Chatelier's principle. Now, the Le Chatelier's principle. This principle states that for a system in equilibrium, if any change is made to the conditions, the equilibrium will alter so as to oppose the change. It can also be stated that if a system in equilibrium is subjected to a constraint, it will adjust to annul or nullify the effect of the constraint. Now, let's now see this principle with those factors that affect the equilibrium. Now, Le Chatelier's principle and the concentration change. If the concentration of one substance is increased, the reaction will move in the direction to use up the added substance. If the added substance is a reactant, the reaction will move in the product direction, and if it is a product, the movement will be in favor of the reverse reaction. If the concentration of one substance is reduced, the reaction will move in the direction to produce more of the substance removed. If the removed substance is a reactant, the reverse reaction is favored. But if the product is removed, the forward reaction is favored. Based on the above, most equilibrium reactions have been made to go virtually to completion by the removal of products as they are formed. Le Chatelier's principle and pressure change. This applies only to gaseous reactions. If the pressure is increased at constant temperature, the system will move in the direction of the reduced volume. Recall that Boyle's law states that Boyle's law is P1V1 equals to P2V2. That is, the pressure is inversely as the volume. The direction of reduced volume is the direction of small number of gas molecules. Recall Avogadro's law. Equal volume of gases at the same temperature contains the same number of molecules. The smaller number of molecules will have the smaller volume. Now, let's say, for example, 2N2 to give N2O2. In the reactant side, we have 2 moles, which is 2 volumes. On the product side, we have 1 mole, 1 volume. Increased pressure will favor the forward reaction, and a decreased pressure will favor the reverse pressure, the reverse direction. When there is no change in the number of gas molecules, pressure will have no effect. Now, Le Chatelier's principle and temperature effect. If the temperature is increased, the reaction will move in the direction that uses up the heat, that is, the endothermic reaction is favored. For a decrease in temperature, the exothermic reaction is favored. Note here that the reaction is in dynamic equilibrium and the forward and reverse reactions can occur. If the forward reaction is exothermic, the reverse reaction will be endothermic and vice versa. A change in temperature will therefore favor the forward or the reverse reaction. The value of equilibrium constant will increase for endothermic reaction but decrease for exothermic reaction. For example, when you look at nitrogen gas reacting with 3 moles of hydrogen to give 2 moles of ammonia, the Kc here decreases with increasing temperature because the delta H is negative. Now, the effect of catalyst on reversible reaction. A catalyst reduces the activation energies for both the forward and reverse reaction. The catalyst does not change the enthalpy of the reaction. In the presence of the catalyst, the reactants and product are not changed. The catalyst only increases the rate of reaction. The equilibrium constant is not changed, but the time to get to the equilibrium position is reduced in the presence of catalyst. Thank you. Now I will pause there so to come back to look at application of chemical equilibrium. Thank you. Welcome back. Now let's move on to application of chemical equilibrium. So we'll look at it in 2 ways: industrial application and application in aqueous media. Now, industrial application. 1. The Haber process, that is the industrial production of ammonia. In Haber process, ammonia gas is produced from nitrogen and hydrogen gases. In this large-scale production of ammonia, the mixture of 1 part nitrogen and 3 parts hydrogen is compressed to a very high pressure, say 200 to 1000 atmosphere, and pass through the catalyst chamber at 450 to 500 degrees Celsius. The catalyst is iron mixed with aluminum oxide, that is the alumina. Now, lowering temperature will increase the yield of ammonia. The iron catalyst is used for the equilibrium to be established more quickly. The production of ammonia is enhanced by removing the ammonia as it is formed. Another industrial application of chemical equilibrium is found in the contact process, that is the large-scale production of tetrahydrosulfate 6-acid. The main reaction is the catalytic oxidation of sulfur 4 oxide to sulfur 6 oxide gas. This is a reversible reaction accompanied by evolution of heat. The catalyst is vanadium 5 oxide, that is V2O5. The method used to push the reaction in favor of the product are as follows. 1. Atmospheric pressure is increased to improve the yield, and number 2 is that the product SO3 gas is removed as it is formed, and also excess oxygen is used. Now let's go to the application in aqueous media. Number 1, to determine the dissociation concentration of weak acid and bases in aqueous equilibrium, that is the acid and base strength, that is HA, which is the weak acid, let's call it the acetic acid, plus water, so it ionizes into hydrozonium and acetate. So the dissociation constant will now be, for the acid, will now be the hydrozonium ion, the concentration of hydrozonium ion multiplied by concentration of the acetate all over the acetic acid. Now, for weak base, which we can represent as BOH, reversibly as B plus OH minus. Therefore, the Kb will now be written as the concentration of B plus multiplied by OH minus all over BOH. Now, the Kp and K are dissociation constants. The Ka and Kb, are dissociation constants for weak acid and base. Number 2, to determine the pH value of a liquid substance and dissociation constants of water, where we see that when water ionizes into hydrogen ion and hydroxide ion. Therefore, the Kw can be given as hydrogen ion multiplied by the concentration of OH minus. Therefore, pH plus pOH is equals to 14. Now, when an acid dissolves in water, Hydrogen ion concentration increases and pH is less than 7. But when a base dissolves, OH concentration increases, that is, the pOH is less than 7 or pH is greater than 7. Hydrolysis of salts. That's number 3. A solution of an acid will turn blue litmus red, while alkaline solution turns red litmus blue. Some salt solutions are acidic or alkaline to litmus. This is because of hydrolysis of salt. For example, a solution of sodium ethanoate turns red litmus blue, and a solution of ammonium chloride turns blue litmus red. The above observation is explained by a reversible reaction occurring between the salt and water, which leads to alkaline or acidic behavior. For example, sodium ethanoate, when with water, reversibly as ethanoic acid and sodium hydroxide. Sodium hydroxide is a strong base, and CH3OOA, which is acetic acid, is weak acid. The solution is alkaline, that is, the alkaline has the upper hand. Now, for ammonium chloride, when it mixes with water, it is reversibly as ammonium hydroxide and HCl, that is hydrochloric acid. HCl is a strong acid, but ammonium hydroxide is a weak alkaline. The acid has the upper hand, and the resulting solution is acidic to litmus. The concept of hydrolysis is very helpful in explaining such observation as above, and is also in making proper choice of indicator for acid-base titration. Thank you for this session, and I will see you again. Make sure that you are safe. God bless you.